Okay, so let's continue on chapter 1. So last time I talked about calculus of variation, right? So we want to deal with some minimization problems, okay, where the input is no longer just a variable, right? So instead is a function, okay? So we input a function and then we get a corresponding integral, okay, which gives us a value, and we want to minimize that integrated value, right? So remember last time we have two classic problems, right? So one is that I pick a point, starting point, and the other ending point, and then I just construct a path for a particle to slide down, right? So I want to construct the path such that the particle can take the least time to slide down from the starting point to the end point, right? So, and that's the so-called brachistochrone problem, okay? So, and using the calculus of variation, okay, so last time I have talked about the solution, okay, so to this problem is a curve known as a cyclone, right? And the second problem that I introduced, but I didn't solve last time is the so-called the soap beam problem, right? So I have this two circular rings, and then I have a soap beam formed between the two rings, and I want to find the shape of the film, okay, such that the surface area of this soap beam is minimized, okay? So again, right, so the method that we use is using the calculus of variation, where the key result is the so-called Euler's equation, right? So brachistochrone problem is what we had last time, right? So, and then this soap film problem, right? So again, the problem, right, the value is given by an integral, right? And then what we are going to input is y as a function of x, right? So such that this whole integral I want this whole integral to give the minimum value, right? So here, right, so you can see that the integrand that we have is this expression here, right? So that's why I call this f to be x times the square root of this whole thing here, right? So to make use of the Euler's equation, of course, I need to evaluate these two partial derivatives, which I do here, right? So, and then after that, right, so the Euler equation will give me this result, right? So the d dx of this whole thing, which is the partial f partial y prime, right, has to be equals to 0, right? So because the partial f partial y is also 0. So, and then the problem is just to solve this differential equation, right? So, and the derivative of this whole thing equals 0. So that means that this whole thing here is a constant, right? Where I call this a, okay? And then now I'm just taking the denominator to the right-hand side also, right? So, and you can see that I have the y prime on the left-hand side, and then the y prime on the right-hand side also, right? So, but the next step I'm going to do is just to make y prime as the subject, right? So on the left-hand side, and then all I have on the right-hand side would be just function of x. So, and this dy dx equals this function of x, and then the next step is just the direct integration, okay? So here, okay, so you need to do substitution, okay, so to get to the result, but not go into detail here, but the result is that the y is the inverse of this hyperbolic cosine function, okay? And that means And that means the x is this hyperbolic cosine function of y. So let me show you again the picture, the coordinate system that we use. Right, so the coordinate system that we use is like this. Right. So if I'm going to draw again the two rings here, right, so that means that like this, right? So this is the x-axis, this is the y-axis. So now that I have this thing here, so what I have over here is the following. So something like this. Okay, it should be symmetric. Okay, so I have this curve here, and then you do a revolution, right? So you could imagine that you get a whole shape like this, right? So in fact, one thing interesting is that if I just look at this curve itself, right? So that is this one, okay? And actually, this shape and this shape over here is the same, okay? So what I have over here, right? So you can see that I have a chain, right? So and then I have two fixed support points, and then if I just let the chain hung by these two support points, this is the shape of the chain that you got, right? So if the whole thing is under a constant gravity, okay? And in fact, this kind of shape is known as, it's called the catenary. Okay? And in fact, I'll come back to this particular problem later. Okay? So here you can see that I have some constant a and b, right? So due to the integration that we had to do, right? So and of course, at the end of the day, the constants will be determined by the so-called boundary condition, right? So because the curves, right, has to touch these two endpoints, right? So which I call this xi yi over here, and then this xf yf over here, and then you can determine a and b. Okay. So these are the two very classic problem that we have just introduced, right? So here I'll give you one more example. Okay, so I want you to maybe take a couple minutes to think about by yourself. Okay. So the problem is the following. Okay. So here I have, you can see this picture here. I have a curved surface. Okay, so this curved surface is given by this equation. Okay, so it's z equals x to the power 3/2. Okay, and then I have 2 points. Okay, so over here I have 0, 0, 0. And then right here, I have 1, 1, 1. Okay, so 2 endpoints fixed. And then the minimization problem that I want to ask is that I want to find the line. Okay, so which lies on the curved surface and has the minimum length. Okay, so that connects this point and this point. Right, so you can imagine that you have infinitely many choice again, right? So it can be like this, it can be like this, right? So many different choice. Okay, so but again, so all the choice that you take has to lie on this curved surface. So and I want you to find the shortest one. Just take maybe a couple minutes. I'll talk about right. So of course, the first thing that you do is to set up the integral, right? So this is the first step, to set up the integral. That this time, right? So the arc length, this differential element of the arc length, again, I will call this ds, right? So this small section over here. But this time the ds is equal to square root of dx squared plus dy squared plus dz squared, right? Well, as in the previous example, I only have dx squared plus dy squared. So now I also have the dz squared. But remember, right? So this is not actually a more complicated problem, because at the end of the day, the z and x follow this relation, right? Okay, so here the first step I would do is that first of all, I really want to pick a variable first, right? So that I can say that this is an integral over something, right? So what I'm going to do is to make it as an integration over x. So that is, I'm going to write it this way. Okay. So this is an integration over x. So now, I told you that, right? So any curve that we pick, right, has to lie on this plane z equals x to the power 3 half. So that means, right? So this dz dx over here can be expressed in terms of x as well. Right? So because this dz dx would be equals to 3 divided by 2 times x to the 1/2. So then I substitute this result to the integral, right? So then I just write integral of 1 plus y prime square, right? I just call dy dx to be y prime plus the square of this dz dx, which is 9 divided by 4 times x dx. So and we know the upper lower and upper limit, right? So because I told you that the one of the point is 0, 0, 0, and the other is 1, 1, 1, right? So then x is just go from 0 to 1. Okay. So that means, right? So we have set up the integral already, right? So and this is the function f that we have. Is this the integrand, right? Okay, so now Euler's equation, right? So Euler's equation, let me recall Euler's equation over here, right? So partial f partial y minus d dx partial f partial y prime equals 0. So first you can see that partial f partial y is 0, right? So and then partial f partial y prime is taking the derivative of this whole square root thing. So let me just write it here, right? So d dx partial f partial y prime is just equals to d dx of this one. And this whole thing has to be equals to 0. Right? So then up to this point, right? So the way mathematically, the way we solve it is very similar to the previous example, right? So this d dx of this whole thing to be 0. So that means that this whole thing here has to be a constant, right? So that means this y prime has to be equals to a constant times this square root in the denominator. Okay. And then I need to rearrange the terms. Again, I want to make all the y prime to be as the subject. Okay. And then just put everything else on the right hand side. Okay, just I skip the manipulation here. Okay. And then what you need to do next is to just integrate both sides, right? So the final answer is just over here. So here I just write this c in terms of this a, just another constant, right? So now here, because I integrate one more time, then I got out another constant. So then this is the solution. Okay, so and what's next that you need to take care of, right? So you need to figure out the constant a and b, right? So by just making sure that this thing, right, passes through the two endpoints, right, 0, 0, 0, and 1, 1, 1. So then this is the solution. Okay, so but not quite complete, because of course y equals x something x, right? So y is a function of x in the three-dimensional space. It will also be some sort of a curved surface, right? But I just want one line, right? So that means, right, so if you specify the line that you have, of course you also need to write down the other constraint that we originally have, right? So this would be the solution. Okay, so of course you have a bit more practice in the homework one and also the exercise class next week. Okay. Okay, so now let's move on to the next part of chapter 1. Okay. So here I want to briefly talk about the so-called the Fermat's principle of least time. Okay. So this is not along the main line of our content, I would say. Okay, so but I want to mention it. Okay, so because this one is interesting, and also this actually historically, right? So before the calculus of variation was invented, right? So and the brachistochrone problem was already solved even before that. Okay, not really using calculus of variation. Okay, so but one of the early solution, okay, so was using this so-called the Fermat's principle of least time. So what is Fermat's principle of least time? Okay. So Fermat's principle of least time is actually talking about the propagation of light. Okay, so we go to talk about the propagation of light for a second. Okay, so move away from mechanics just for a second. Okay, is that so? I believe you do have the basic knowledge about the propagation of light, right? So you know that first of all, in free space, you know that a ray of light propagate in straight line, right? So and then the other thing that you would know is that if a ray of light hits a mirror and it will get reflected, right? So the ray of light go from air to water, right? So it will have reflection. So you know this basic propagation, you know reflection, you know refraction, right? And if I just show you these two pictures, right? So I'm sure that you know this law of reflection, this law of refraction, right? So, or the so-called Snell's law, right? So know that for the law of reflection, what you have is that the so-called angle of incidence equals the angles of reflection. Right? So and then for the law of refraction, right? So what you have is that the so-called n1 sine theta 1 equals n2 sine theta 2. So and so why this angle of incidence is equal to the angle of reflection, and why this incidence angle and this refracted angle will related by the Snell's law. So and what Fermat said that is that the path, okay, taken by a beam of light, okay, so between any two given points, okay, is the path that can be traveled using the least time. So if I just go back to the most simple case, right, just the light propagate in a straight line, right? So that one is easy to understand, right? So if I have this point A and this point B in free space, right? So then among all the paths that the light can choose, right? So then of course the straight path would be the one that that allows the least time, right? So and now about the law of reflection over here, that suppose again I pick this starting point, right, and then this ending point, right? So and then suppose I require that the light, okay, has to bounce off from this mirror surface once, right? So and then travel to B, okay. So then, but still, the lights can have many different choices, right? So it can goes like this. Okay, it can goes like this. Right, so it goes like this, and so forth. Right? And it turns out that, right? So from this picture, right, you could kind of see that different choices will lead to different total length, right? So and that leads to different travel time. And it turns out that to have the least travel time, okay, so the angle that you have to take has to be this angle of incidence equal to this angle of reflection. Okay, it has to be this one in order to have the least time. So similarly, for the refraction problem, okay, so again, I have this starting point here and this ending point here, right? And then I ask the same question. Okay, so which path can the light take, okay, for it to spend the least time, okay, to complete the journey? Right? So again, you can have many different choices. Okay. So in this case, well, you kind of understand the strategy actually, right? Because, well, now we have two different refractive index, right? So you know that, let's say the N1 is the one with the higher refractive index. Right? So that means light travels in this region slower, right? So the light travel in this region faster. Okay. And because of that, when you pick your path, you somehow kind of want to make the first part of your journey, the first length here, to be actually shorter, right? So because this is the part that only allows you to travel at a slower speed, right? And then if you pick a shorter path over here, of course, it is unavoidable that you have to pick a longer path in the second section. So that's why, right? So it turns out that, right? So you want to spend a shorter path over here and then a longer path over there in order to take the least time. Okay. But it cannot be too much, right? So if you take this path, for example, although the first path will be further shortened, but then the second path will becomes really long. Okay. So here, okay, so let's actually try to do, okay, so using the Fermat's least time principle to actually try to kind of derive the so-called the Snell's law. Okay. All right, so what I have is over here. Okay. So again, right, so starting point, end point, right? So and then I'm free to choose any point along this boundary. Okay. So if I want to calculate the total time, right? So first, want to calculate the time taken for this path, right? So which is just the length of this path divided the speed of light in this region, right? So the length of this part over here is the square root of this thing here, right? And then the speed of light in this region, right? The speed of light in this region, which I call V1, is C divided by N1, right? And then the speed of light in this region, V2, I call this C divided by N2. Okay. And that's how I got the time for this part and then the time for this part. So then the total time, right? So it's just these two functions added together. And then to find the minimum value, right? So I just need to take the derivative of this total time and set it to 0. Okay. So if you actually go to take the derivative, okay, so what you will find is this N1 divided by C. Okay. So this is what you got. If so here, okay, so in this part, so we are actually we actually forget about the calculus of variation, right? So here I don't even need that, right? So because I'm just talking about varying one point over. So it's just original, just regular calculus that you have used before. Okay, so now if you look at this ratio, right? So this is this one is this length over here. Right, so let me right, so this one is this length over here, right? And then this y1 is this length over here, right? So that's why, so this whole thing is exactly our sine theta 1. And similarly, this one is our sine theta 2. So that is Snell's law, right? So from believing that the light will always pick the quickest path. Okay. So now, okay, so the whole point of mentioning this is that I want to, as I said, I want to tell you how it can be used to again solve the Brachistochrone problem. Okay. So before that, okay, so let me show you picture over here. Okay. Okay. So now instead of having just 2 layers, right? So now I have multiple layers, right? So you could just imagine that there are n layers, and then different layer has different refractive index. Right? So now how the light would get refracted, right? So then you know that you just need to consider layer by layer, right? So when, for example, when the light is propagating from the J layer to the J+1 layer, right? So this propagation over here, right? So should not really depend on the refractive index of any other layer, right? So that's why, right? So if I consider the light traveling from this layer to this layer, right? So then the refraction happens here, and you can again, right? So apply the Snell's law, right? So at this interface, right? So that is this nj sine alpha j equals nj plus 1 sine alpha j plus 1, right? And then after that, right? So when the lights arrive at the next interface, then you apply the Snell's law again. But I think you don't have really problems accepting this, right? So now, right? So what we want to consider, right? So is that taking the limit, right? So again, 2 layers and then n layers, and then just basically taking the continuum limit, right? So what I have over here is that, let's say I have this material, right? So with this continuously changing refractive index, okay? So as a function of x, okay? So then you can see that I have this using this slowly varying color, okay? So to represent that change in refractive index. Okay. So now, if I want to, again, at this starting point and this end point, I want to find out the total time for the light to travel, right? So then the formula that I use over here is what you have seen before, right? So this ds divided by v is this dt. So Then after some manipulation, right? So I am able to write down this total time is the integral of this. So now, up to this point, right? So not much a trick here, right? So and now if I look at it, right? So I can treat it as a problem for calculus of variation again, right? So because now the thing, let's say the thing that I'm allowed to vary, right? So is this path, right? So I no longer just have one point to vary, right? So because there are many layers, right? So and this n of x is given, right? So it's not a varying. Okay, so I just give you this distribution already. So now if you look at this, and if you again go to apply the Euler's equation, right? So then what you conclude is that the derivative of this whole term here has to be equal to 0. And then if you just integrate both sides, then you say that this whole term here is equal to a constant. So now, actually, if you look at this y prime divided by this one, okay, this is again a sine theta. Okay, so it is a sine theta that if you just imagine that you take right, so this is a normal line, right? So you can imagine that you take the tangent of the line at a particular point, and you can form a theta over here. So this is again actually Snell's law. So here I show you that, right? So this is actually using the Euler's equation, right? So using that, showing you that even I have this really rather complicated or spatial varying function of this refractive index. Okay, Snell's law will still hold. Okay, how does it hold? Is that just look at a particular point. Okay, consider that one as a two-layer problem, and then locally, right? So Snell's law will still be satisfied. Okay, but still, right? So if you just forget about this Euler's equation, right? So even with the physical argument that I just gave you previously, right? So you would believe that for this multi-layer problem, right? So I would have this Snell's law to still be true. So that is what I'm saying is that even without the Euler's equation, if you just use this physical this Fermat's principle this time, you can already conclude this. Okay, so now how is it related to the Brachistochrone problem, right? So here I'm going to use a refractive index function that is equals to this one divided by square root of 2gx. Okay. So you see why I want to set this in a second, right? So if I indeed set this refractive index function to follow this dependence, then if I go back to plug into this integral, right? So then the time taken for the light to travel is the integral of this function over here. And now, if you look at this integral, and go back to the Brachistochrone problem, you realize that we are actually dealing with the same integral. Okay. In the Brachistochrone problem, okay, we are also trying to minimize the same integral. So now that the light traveling problem, we have the same integral, and then we know that the solution is given by the Snell's law, right? So, and that's why without really calculus of variation, okay, so using the Snell's law, we know that the minimum solution, the minimum value will be given by the function satisfying this relation, which is the Snell's law. And again, as I said, right, so we have solved it already, right? So using a calculus of variation. So then this is just really another way, right? So even historically, a earlier way, right? So to solve this statistical problem. Okay, so now let's take a break for 15 minutes. And I have still 2 more slides to go through for this chapter, and then we'll move on to actually see how this calculus of variation, okay, is used in the formulation of Lagrangian mechanics. Okay, so let's continue. Okay, so here is the schedule for the midterm test. Okay, just the regular class time and location. Okay, so right here. Okay. So because I know that the week before, okay, so you have the midterm of 3051. Okay, so don't want to get this too close to the other one. Okay. Okay, so up to this point, I have already finished talking about the key method of using the calculus of variation, right? So finding the minimum value of the problems. And before I move on to the next chapter, right? So here I just want to also tell you a kind of a shorthand notation. Okay, so that is commonly used in calculus of variation. Okay. So then the content here is not new. So it is basically just again lay out the derivation of the Euler's equation. Okay, so but just using a slightly a different notation that you might find it more convenient to look at. Okay. So remember what we did when we do the derivation of the for the Euler's equation, right? So we consider that y can be written as the so-called y mean. The y mean is the curve that gives you the minimum of minimum result, right? So, but that is unknown, plus a parameter alpha times some function eta x, right? So that's the strategy that we used before, right? So here, right? So instead of writing this alpha times eta x, so here I'm just writing it the whole thing as the so-called delta y. Okay. So not dy. Okay. So but this delta symbol, this delta y, and then this y prime written at this y mean prime plus delta y prime. And okay, because as I said, I'm not doing anything new, right? So then this delta y and this delta y prime, right? So basically would means this this eta x d alpha, this eta x delta, this eta prime x d alpha respectively. Okay. So And because of that, right, so we can just rewrite this df d alpha, which I call this delta f, okay, as this notation over here. Okay. And what's followed is the same, really is the same procedure. Okay, so but as I said, the notation that has been changed, right? So instead of this delta alpha eta, I will have to write this delta y and delta y prime. Okay. I don't want to actually spend much time over here. I would like you to have a look. And in fact, later after we get to the Hamiltonian mechanics, so maybe at that point, I will go back here to review this, because at that derivation, you might find it really more convenient to use this delta notation. But at this point, it doesn't really affect you, but I just put it here as an appendix for now. Okay. So, but here, let's move on to the next chapter. Okay. So chapter 2 is on Lagrangian mechanics, right? So I think in the introduction last time, right? So I told you that, right? So instead of starting from the Newton's second law, right? So here we use a different perspective, right? So is that we have a particle moving in a certain trajectories, and then we are trying to minimize a physical quantity of that certain trajectory. Okay, and if that quantity is minimized, then that would be the correct trajectory. So, and that would be known as the principle of least action. Okay, or some people just call it principle of stationary action. Because after all, right? So you can see that in the last chapter, so when we were finding the so-called minimum, right? So we only really taking the first order derivative, right? So you could ask the next question, okay, taking the first order derivative is 0, but how do I know that this is a minimum? It could be a maximum or other stationary point, right? So, but it turns out that, right? So in the previous examples that we have, okay, if you really try to test that, the solution we had indeed give you the minimum result. Okay. Okay, so let's talk about particles. Okay, so moving. So I start with this simple case, right? So where I just have a particle moving in one dimension. Okay. So then moving in a straight line. So I call this x, right? And then suppose at some initial time ti, right? So it starts at some initial position xi. Okay. And then at the final time tf, okay, it arrives at this final position xf. Okay. So now, right? So the curve, I've drawn a few curves in this plot, right? So of course some of the curves, they are not straight lines, right? But you understand that in this representation, right? So the particles are actually moving in a straight line anyway, right? Because I told you already, it's just a one-dimensional problem now. But then you understand that the slope of the different curves will corresponding to the different velocity and acceleration of the particle, right? So for example, if I really pick this straight black line, right? So you know that means that my particle is moving at a constant velocity, right? So all the way along, right? And if I pick this purple path, that means that initially the particle is moving very slow, and then it accelerates, right? So and then we move at a very fast velocity until it arrives at end point. So, but anyway, so any of this curve, right? So I can just call this x as a function of t. Right? So now I'll define, or not define, but I'll just have this two quantities that you know already, right? So is that I have at any time t, right? So you know how to calculate the kinetic energy, which I call t, right? So as long as I give you the x as a function of t, right? So you can calculate the velocity, then you can calculate the kinetic energy. And also, right? So I can calculate the potential energy, right? So at well, you know that potential energy, at least for the kind of potential energy that we have learned, right? So it depends on position, right? So then I give you the position as a function of time, then you can tell me the potential energy as a function of position or as a function of time. So now here is the quantity that is defined as that is known as the Lagrangian, okay, and it is defined as the potential energy minus, the kinetic energy minus the potential energy. Okay. So this quantity is called the Lagrangian, this capital L. Okay. So and next, okay, so the action is defined as the time integral of the Lagrangian. Okay. So of course, the time integral will be taken from the initial time ti, right? So to the final time tf over here. Okay. So and now, right? So this L, right? So you can see that it's a function of x and x dot, but of course x and x dot also function of t, right? So then this at a particular time, right? So you can calculate the Lagrangian L, right? So then you can plug it in to this integral. So now you could imagine that, right? So although we are not really calculating them, but for different curves, right? So you will have different action. Right? So even if you just forget, although in this curve, in this figure, you cannot really tell the information of the potential energy, right? So, but even in the simplest case, right? So you could just set this u equals 0, right? So you just imagine that you have this kinetic energy term alone, right? So you just, if you try different x of t over here, and then you plug it in, right? So you find that the s for this curve would be not the same as the s of this curve, and not the same as the other as well. Okay. So again, right? So imagine that you have infinitely many choices, right? So as long as your path, right, start at this point, at this time, and end at this point and this time, right? So you have infinitely many choices. So now here it comes to the principle of this action, or we call it the Hamilton's principle. Okay. Is that right? So it's over here. So of all the possible paths, right? So along which a particle may move, right? So from one point to another, right? Within a specified time interval, right? So from ti to tf. Right? So the actual path followed is that which minimizes the action s. Okay. So now you see that this becomes again the problem in calculus of variation. Okay, so that's why we'll need the Euler's equation. Okay, so here. So in the last chapter, right, just half an hour ago, right, so we are minimizing more like this one, right? So here we are minimizing this one. You can see that we were integrating over x, but now we are integrating over t, right? So then the curve that we had before is y of x, and here is x of t, right? But just changing the variable names, right? So you see that, okay, so the Euler's equation just becomes this form over here, okay? So that is, right? So the path has to satisfy this relation here. And this is known as the Lagrange equation of motion, okay? So, or we call this the Euler Lagrange equation. So, in this equation, clearly it would be a differential equation. Right? So you could imagine that at the end you will have some x, and then some x dot, and then some derivative of x dot maybe, right? So then this will you'll soon see very soon is that at the end, right? So the differential equation that comes out from this Lagrange equation of motion will be consistent with the differential equation of motion that you obtain from Newton's second law. Okay. So and here is show that it is indeed the case, right? So I start from the Lagrange equation over here, right? So remember the Lagrange equation, Lagrangian is defined by the kinetic energy minus the potential energy. Okay. And in the first term, right, so for the partial derivative, right, so you know that this kinetic energy is 1/2 mx dot square, right? So but this partial x, not partial x dot. So that's why the first one, well, only the partial u, partial x survive here, right? So partial t, partial x is just 0. And then on the other hand, okay, so the second derivative here was this t minus u, but this time is taking the derivative with respect to x dot, right? So but the u, the potential energy, right? So at least the potential energy that we are mostly talking about would be just a function of position only. Potential energy is not a function of velocity, right? So you have this Coulomb potential or this gravitational potential, right? Is this 1/r, right? And this r is the distance between your source and your particle. Right? So potential energy depends on the position of the particle, right? But the potential energy does not depend on how fast your electron or your charged particle is moving. So that's why for the second term here, right? So this partial u, partial x dot will just be 0. So and then here, right? So you need to further go to actually take the partial derivative. You see that the whole second term here will become m times x double dot, which is m times a, right? And then plus this du dx. Okay. So here I don't use partial symbol anymore because as I said, this is a one-dimensional problem. So u is a function of x only anyway. So then you can see that now I have this mx double dot plus du dx equals 0. And remember that the definition of this potential energy, right, is that the force is given by minus du dx. Okay. So that's why, right? So this equation really is nothing but F equals ma. Okay. So you can see that how the Lagrange equations and the Newton's equation, the Newton's second law, are equivalent to each other. So of course, here I just go from one way to another. I go from Lagrange equation and arrive at Newton's equation. Okay, and you can actually do the other way around. Okay, so but for that derivation, okay, so from Newtonian mechanics, you want to derive Lagrange equation. Okay, so you can also you can just go ahead and see the textbook. Okay, so because here the focus, at least for us, is that we only want to focus on how this Lagrange equation, okay, comes from the least action principle. Okay, we don't focus on how the Lagrange equation can also be derived from Newton's equation. Okay. So now some simple example over here. Okay, so I'm sure that all these three cases are the physical system that you have dealt with before, right? So free particle, then your kinetic energy, okay, minus potential energy. Potential energy is 0, right? So in that case, you have this L. Then if I want to plug it to the Lagrange equation, right? So you just need to take these two derivatives, and at the end, right? So the solution, right? So the x of t that satisfies the Lagrange equation would be this mx double dot equals 0. And again, that would be the same as the Newton's second law, right? So the Newton's second law will also tell you this: the acceleration of the particle is 0 without any. You are not in a potential field, or you're not in a potential, right? So there's no force. And now this next one, right? So something that sure that you have learned also is that I have this particle in uniform gravity. Okay, so now this time, right? So the particle, again the kinetic energy is always just 1/2 mx squared, right? So and this time the potential energy, this one. Okay. So then if you go ahead and do the derivatives, right? So this time you'll find that this m the force is given by this mg. Okay. So one more typical example you have learned, right? So the simple harmonic oscillator, right? So but this F equals to minus kx, and for that the potential energy is 1/2 kx squared, right? And with that you'll see that this ma equals to minus kx, so which is the force. So now you'll see that the two equations, right? So really give you the same result, right? So at this point, right? So after you arrive at this equation of motion, right? So then the next is the same as what you did before, right? So solving the differential equations, right? So really would just follow the procedure of what you have learned before. Right? So next, need to talk about, okay, so some problems that are more realistic, right? So is that I have this 3-dimensional motion over here that I have. Now I have this path to be defined as this x as a function of t, y as a function of t, and then z as a function of t. Okay. So and now the kinetic energy, okay, so would be this one, right? And then the potential energy, this one now. So and the Lagrangian is still defined in the same way. Is that the kinetic energy minus the potential energy. Okay. So but now I have this 3 coordinates or 3 variables is the x, y, and z. Okay. So and then the action is still defined this way. So however, right? So in the chapter 1, right? So I actually need to go back to chapter 1 because in the chapter 1, all I was talking about is just function of this one variable, right? So now I have different independent variables. So how do I go to deal with this kind of minimization problem? So that is the one last piece that I now go back to here is that in fact in calculus of variation, okay, so it is also capable to deal with the case where you have multiple independent variables. Okay, so the form that we had before is always like this, right? Just one variable, or really the variable really means a function or path, right? So it's just y as a function of x. Right? And now if we consider a problem with two independent variables, right? So and the reason, right, so we care about this is something that you have just seen, right? So if I want to consider a particle in two-dimensional or even three-dimensional motion, right? So here, let's say two dimensions. Okay. So then we care about this minimization problem, right? So with these two y1 and y2, two functions, okay, and both of them, both y1 and y2 are functions of x cost. Okay. And in fact, the nice thing is that it turns out that the strategy that we had for one independent function, okay, can be trivially extended to two or even more independent variables. Okay, so before, right, so I have this, say that this y equals to this y mean x plus alpha eta x. Right. So here I'm basically doing the same thing, right? So, but it's just that now I have this eta 1 and eta 2 instead. Okay. Again, eta 1 and eta 2 can be anything, right? So, and in general, this eta 1 will not be equals to eta 2, right? So, but the nice thing is that we don't really need to know exactly what they are, right? So we just need to care about this parameter alpha. Okay. So, and now, right? So of course the eta 1 and eta 2 again have to satisfy the boundary condition. Okay. And we use this alpha, right? So just like before, right? So basically to instead of really exhausting all the possible functions, right? We just need to understand, right? So the change of this, how this J change of this variable, change depending on this variable. And if I again, right, so take the derivative actually, right, so and using the same chain rule, although now I have two more terms, right? But the nice thing you can see is that although it looks more complicated, right? So but the nice thing is that the eta 1x, okay, and the eta 2x, the two groups of terms, okay, can be really just stand side by side and don't have any cross term. Okay, so they are really can be completely separated, right? So then if I want to look at this integral, right, so I can just treat it as a two integral. So the first integral for this one, the second integral for this one, right? So if just look at these two terms, right, so you can just apply the integration by part technique that I showed you last time, right? So if you look at the second group of terms, you also can just use the integration by parts technique, right? So that is using integration by parts for the first group, using the integration by parts for the second group, then you will have you'll be able to write down this first group of terms, which is only with this eta 1, and then this second group of terms, which is only with this eta 2. Okay. And now, right, so the nice thing is that this eta 1 and eta 2, they can be anything, and they are not correlated, right? So they can be completely independent, right? So, and because of that, we can argue that this one and this one, each of them has to be simultaneously zero, right? So in order to have this whole thing to be zero, okay. So because of the fact that this one and this one are two independent arbitrary functions. So that is, the nice thing is that we have more independent variables, but then we just need to write down more Euler's equation. But you can see that each of the Euler's equations just look the same, right? So you have, even if you have n variables, right, you just need to write down n Euler's equation, right? The exact same form as what we have for the one variable. Okay, so that's why, right? So here, right? So how many independent variables we have? That will be 3, right? So it's this x, y, and z. Okay. So that is, in this case, well, maybe it's probably not surprising to you, is that we will have to write down 3 Lagrange equations of motion, right? So Lagrange equation of motion for x, right? Lagrange equation of motion of y, Lagrange equation motion for z. Okay. And then if you again go ahead and actually take the derivatives, right? So what you have would be the 3 equation of motions, right? So, and this 3 equation of motions would be the same as what you got, right? So if you consider the x component of the force, the y component of the force, and the z component of the force, right? So here, again, one example, right? So I want you to look at this projectile motion, right? So under constant gravity, right? So this is a 2-dimensional problem, right? So then we need x and y, so 2 equations of motion, right? So in Newtonian mechanics, so what you have, consider, what do you need to consider, right? So x component of the force and y component of the force, right? So in the x direction, right? So there is no force, right? So the mg is going along the y direction. In the y direction, this minus mg. Okay. So then then that's it, right? So how to solve this? It's just you just need to integrate the 2 equations twice, right? So and of course, whether you get this parabolic curve or you just get a straight line up and down, right? So that really depends on the initial condition, right? So that has to be specified. Right? So but here, okay, so we just write down the equation of motion. That's good enough. And Lagrangian, right? So then I have this T minus U, right? So the potential energy, right? So because of this 2-dimensional case, I will have to write down this Vx squared plus Vy squared. So, and then the potential energy is minus mgy. So now apply the Lagrange equation twice, right? So for the x direction and the y direction, then you realize that, okay, so of course you got the same thing as the Newtonian equation. Okay. So applying this Lagrangian method, okay, is actually quite handy, right? So you just need to write down the potential energy and the kinetic energy. You don't need to worry about the direction of the force explicitly. But of course, right? So there is always a price to pay, right? So because the key is that first of all, you need to know the potential energy, right? But how do you know the potential energy, right? So at this level, right? So we have to know the force, right? So if I don't tell you that the force is mg, right? So then you really don't know how to write down the potential energy as mgy. But just that after you have defined the potential energy well, then it's very convenient. Okay. So, and another nice thing, okay, about this Lagrange equation is that the form of the Lagrange equations, okay, so the independent of the coordinate system that you use, okay. So here I'm trying to talk about the Cartesian coordinate and polar coordinate system. Okay, maybe I will just again give you a quick review on the two coordinate systems, because you probably have learned it in the last semester, but let me just spend a few minutes on this. Right. So Cartesian coordinate system, of course, you have these two numbers, this x and y, right? So and then your unit vectors will be the one pointing in the x direction, x hat, and the other one pointing in the y direction, y hat. And then for the polar coordinate system, right? So how do you specify the position of a particle, right? So is that if I have a particle over here, right? So the two numbers that I'm going to specify is that first of all is the distance between this particle and the origin, right? Which I call this r, and then also the other coordinate is this theta, right? Is this angle between this r line and the x-axis, right? So this is xy, this is r theta, right? And but well, that's the easy part, but the way that we define the unit vectors in the polar coordinates, remember, okay, it's actually more complicated in some sense, right, compared with the Cartesian coordinate system, is that the unit vector of the two for the two variables, okay, so actually change directions as a function of position. So you can see that in my picture here, right? So if my particle is over here, then the r and theta points in the two directions like this, right? So and if the particle is here, then the r theta hat direction point in two different directions. So but the key, as you might remember, is that the r hat always points away from the origin, right? And the theta hat always point in the direction that is perpendicular to this r hat. So this is how we relate this r hat and theta hat, okay, with this Cartesian coordinate system. Okay, but the key is over here, is that I want to talk about the motion of a particle, right? So not just the position, right? So but also the velocity over here, and also the acceleration. Okay, sorry, this all should be r. So and in the Cartesian coordinate system, right? So you know that is this form, right? So that is the one that you're familiar with, right? So but on the polar coordinate system, right? So it is just r times r hat, right? So r is this length here, right? And this r hat is this vector over here, right? And the complications arise when you take time derivative, right? So in the Cartesian coordinates, because the x hat and y hat are just constant and are independent of the position of your particle, so that's why when you take derivative, then you just need to take derivative for this x function and y function. Okay. But in this case, okay, so as I said, because this r hat really depends on the position of a particle, so as you move, the r hat also changes. So that's why if you take the time derivative for your position vector here, right? So you need to really take the whole thing, right? So you need to take into account of the change of the unit vector itself as a function of time, right? So then here you can see that I am using this chain rule over here, right? So the first one is that take the derivative of r of t times r hat plus r of t times the derivative of this r hat itself. Okay. And how the r hat and also the theta hat change with time are given here. Okay. So, and at the end, you see that this drdt, okay, will have this r dot r hat plus r theta dot theta hat. Right, so the two components comes out, right? So the velocity along the radial direction, right? So, and also the velocity along the tangential or the transverse direction. So, and then this d square rdt square, right? So you actually need to take this whole thing and then take the derivative again, and you get this complicated expression. Okay. So now, okay, so this is the one that we'll need to use over here, because ma, right? So md square rdt square in polar coordinate will be written as this way. So here, I will talk about Lagrange equation, but let's go to Newton's equation first, right? So in Newton's second law, right? So if you apply this, right? So in this 2D problem, right? So in Cartesian coordinate, no problem, right? So you just need to take the x component, y component individually. Right? So but now, right? So in the polar coordinate system, right? So if I write down again the f equals ma, right? So you can see that the expression is over here. Okay. Now, you can still break it down into two components, right? It's the r hat direction and the theta hat direction. And the two equations of motion that you'll get will be these two, right? So not these two, right? So all I'm saying is that after you change your coordinate system, right? So to have this new pair of variables, right? So in this whole pair of variables looks like this, looks very nice. But after you change it, you don't just get what I'm writing down over here, right? Right, from xy to r theta, after you change to r theta, you don't just get the same form. But instead, you will get this more complicated form over here. Right? So that is the form of the differential equation, right? Okay, will vary. Okay, so with respect to what coordinate system you use. Okay, okay, but here in the next chapter, okay, so you'll see that although here it looks more complicated, but in some particular problem, which is known as the central force problem, you'll find that solving this set of equations actually more convenient than solving this set of equations. Okay. But that's the details that we need to talk about in the next chapter, but not in this chapter. Okay. But all I'm saying is that, right, so you see that the form of the equation, Newton's equation, are invariant. Okay. However, that's not the case for Lagrange equation. Okay. So again, if I have this particle in 2D coordinates, okay, so then this is, first of all, of course, the when you write down the kinetic energy and potential energy, okay, of course, the form will be different, because the x dot and the y dot has to be converted into the derivatives in the polar coordinate system. But regardless, right, so L is just KE minus PE, right? So in Cartesian coordinates like this, polar coordinates like this. Okay. However, once I write this down, right, so the Lagrange equation, you can see the form of the Lagrange equations in the two coordinate systems, okay, are actually the same. Okay. So I just replace, you can see that I just replace this x, okay, by r, and then replace this y by theta. Right. So, and as long as, right, so these two are two independent variables. Right? If you further change to another coordinate system, right, so you use a pair of new variables, another, maybe call this u and v or whatever, and that if u and v are also independent variables, then you just replace this r by u and then replace this theta by v. Okay. Right, so you can see that the Lagrange equation, you can see that in this sense, right? So it would be easier to set up. Okay. However, does it mean that at the end of the day, we got different equations of motion if we use Lagrangian mechanics and Newtonian mechanics? Of course not, right? Because here is just the starting point, right? So if you actually plug this Lagrangian back to the Lagrange equations, right? So at the end of the day, you will still get the same two equations of motions that looks exactly the same as what you have got in the Newton's law. Okay. So at the end of the day, equation of motion, same. Okay. I think it's a good point for me to stop here for today. Okay. So next week we'll continue.